Today I want to talk about math in computer science education. More specifically, I want to talk about why you learn so much math during the computer science program, especially since people believe that they are unlikely to actually use it in industry. I will be honest and not drag out the answer itself. The main reason is that mathematical problem solving is incredibly applicable in many facets of life, including on the job as a software developer. Oh, and this entire video was actually inspired by this comic from Pearls of Raw Nerdism that I saw a while back. So without any further ado, let's dive right into this video. Most people that are just getting exposed to computer science for the first time tend to ask the question, why do I have to take so many math courses in computer science upon seeing their degree planner? Actually, it's not just then, given that I heard people ask this question an enormous number of times over my 3 years of TAing a CS course. Anyways, the degree planner for CS will generally have around 6 math courses and 2 statistics courses required to graduate. These courses typically include Calculus 1 through 3, Linear Algebra 1 and 2, and lastly, a discrete math course. This seems like an overwhelming amount at first, but many CS students end up taking extra math classes by the end of their degree as they recognize the usefulness of their math classes, or just because they find some topics particularly interesting. So let's ask the question again. Why so many math courses in CS? Almost a fifth of your degree has to be just math and stats. The answer is that low-level mathematics courses intend to teach you a mathematical approach to problem solving. You may have heard this being thrown around as the answer with no further qualification and may have even gotten frustrated at that. What the hell even is a mathematical approach to problem solving? Well, let me answer that for you. In your linear algebra and discrete math courses, you will inevitably encounter mathematical proofs. Proofs are honestly the best example of mathematical thinking. In essence, in a proof, you're trying to show how a certain property of a system holds given a particular set of initial conditions. Additionally, you cannot submit a proof that hand-waves all the details away and hope for a good grade. No, you must use what you already know about the initial conditions to make a logical statement that gets you closer to the conclusion you want to reach. However, it is unlikely to get you all the way, so you repeat the above process of applying what you know to the intermediate statements, repeating over and over until you either give up or hopefully get to the conclusion that you are seeking. Additionally, you have to clearly state any assumptions that you made and justify them, since if you do not do so, you will get a lower mark. This is precisely what mathematical thinking is. Being able to apply a particular tool that you have to a subproblem in such a way that gets you closer to the solution of the overall problem. Additionally, it is a systematic approach that rewards you for making your assumptions clear. This sort of methodical approach to problem solving is incredibly important in computer science and even beyond. After all, the same methodical approach is useful in both proving that the square root of a prime number is irrational and convincing your coworkers and project managers that your design will not lead to deadlock in a multi-threaded application. So, I am sure that you are convinced that proof-based math courses are useful, but what about those pesky calculus courses? I mean, there are rarely any proofs there. You are simply given an equation and you're expected to just evaluate it. Compared to the elegance and precision of a good mathematical proof, this can't be just as important, can it? Well, it is. After all, finding the equation of the slope of a function or finding the volume of an object given the equation for its cross-section exercises your mathematical thinking just as well as a proof does. After all, you start with an initial problem, then you notice a pattern and apply some mathematical rule to it to simplify the equations. You again keep repeating this cycle of pattern recognition and simplification until you arrive at an answer. All the simplifications you have done and written down are basically the proof itself that the original equation is equal to the final result you have achieved. This is again why teachers and professors keep saying, show your work, and give you a lower grade if you don't. Alright, that should cover all the basics for why math courses are required to get a computer science degree. However, one thing that some students don't really realize until they are deep into their CS program is that CS itself is completely filled with math courses in disguise. Let's talk about that next. Oh man, I always found it a little bit funny when people would get blindsided by proofs and math popping up in courses like operating systems or computer networks. In CS, no course is truly free of math. How come? Well, it's because math is just straight up useful all over the place. Whenever anything needs to be done optimally in some topic, mathematical optimization becomes relevant almost immediately. Whenever correctness or runtime bounds need to be proven or calculated, again, math just becomes irreplaceable. And keep in mind, proving correctness and calculating runtime bounds comes up in basically every CS course under the sun. So, with that in mind, I will list all the courses that you will encounter that most people don't realize are just math courses first, and then list out all the courses that people colloquially know to be math or statistics courses with a sprinkle of computer science added for taste. As already mentioned, let's begin with a list of courses that are surprisingly just math courses. These courses are the design and analysis of algorithms, advanced algorithms, computer graphics, and lastly, the theory of computation. Let me justify this list a bit. In your course on the design and analysis of algorithms, you basically apply all your discrete math knowledge to learn new algorithms along with proving properties and runtime bounds of said algorithms. Usually, these courses have next to no programming, just proofs and calculations. The same can be said about advanced algorithms. Next is computer graphics. This one is not too surprising to some, as computer graphics is all about computational linear algebra, and that's mostly it. You spend a lot of time figuring out how to tile surfaces, rotate objects, find line or surface intersections efficiently, and more. You also learn about quaternions, and most exams are either math proofs or solving equations. Last but not least is a course on the theory of computation. This course is simply your discrete math course, but on steroids. Computational models and language theory are all about logic and state machines, which are, in essence, a mathematical construct. Additionally, the course evaluation is done through you writing tens of proofs, so there is that too. Alright, we need to swiftly move on to a list of courses that are basically just math courses, but with some light CS flavoring. The absolute obvious one is numerical methods. I mean, it's quite literally in the name. Next is machine learning, which is basically computational linear algebra and vector calculus applied in the context of statistics. Another one is reinforcement learning, because most of the time is spent on analyzing the mathematical effectiveness of different models. Right along with it is AI, which is basically attempting to optimize a brute force state space search through heuristics. Oh, while we're here, computer vision is basically machine learning applied to the problem of image recognition. Moving away from ML and AI for a moment, I need to briefly mention computational cryptography and cybersecurity courses. These courses are basically calculus, number theory, linear algebra, and field theory standing on top of each other dressed in a trench coat. The math tends to be particularly mind-bending in those courses. The last course that is basically just an applied statistics course is performance modeling, where you use convex optimization, stochastic processes, and queuing theory to try and model the performance of some complex systems. Performance modeling is actually the part that comes up in computer networks and operating systems, which tends to throw people off during exams. It throws people off mostly because the mathematical rigor that the professors expect from you is significantly higher than the students' expectations are set to. As you can see, across all the courses I have mentioned, and I mentioned a total of 14, math is an important part of each of them. This is in part because a lot of the courses are based on math itself, and in other part, it's because math and mathematical thinking are just such powerful tools for expressing incredibly complex relationships between different systems. After all, computer science started as just a field of mathematics, and only later evolved to what it is now, the evolution spurred on by the pervasiveness of technology in our day-to-day lives. That is why it shouldn't be particularly surprising that so much of CS is basically just math. So, with that in mind, I think we can now discuss whether or not all this math you learned during your undergraduate CS program is of any use beyond your undergraduate education. Let's get to that, shall we? Once you are done with your undergraduate program, you have two choices: remain in academia or leave academia. Let's begin by talking about what happens if you stay in academia. If you end up staying in academia, then you are likely to keep studying some complex topics and dive deeper and deeper into some area that you found interesting either in undergrad or in the few graduate level courses you end up taking. These complex topics will typically have a lot more math in them because both academia in general and the researchers that publish papers in CS tend to like mathematical formalism. Therefore, if you do your graduate studies in most topics in CS, you will not escape math, making it a very useful thing to know that you will almost definitely end up using. However, what if you're dead set on doing research in some topic where there is basically no mathematical formalism, something like human-computer interaction or even software engineering? Will you need math then? The answer is actually yes, but in a different way to before. While it is true that there is much less mathematical formalism in those disciplines of computer science, doing research into these topics tends to be a lot more experimental. Additionally, in academia, you are expected to publish papers showcasing your research. And in order to get into a journal, you need to have your experiments and experiment results accepted by the journal reviewers. The only way to do so is to use standard accepted scientific approaches, which involves analyzing your results for statistical significance. Since statistics is also mathematics, you will be expected to use mathematics in this way. So, as you can see, if you remain in academia, you will not be able to completely escape using math, so it'll obviously be useful. Anyway, there are actually few people that end up remaining in academia after finishing their undergraduate education, especially in computer science. After all, the software development field is quite lucrative at the moment, so a lot of people try their hand at a career in tech after finishing their computer science degree. Okay, back on topic. If you go into any field related to machine learning or data science, you will be expected to deal with a lot of math. No surprises there, and definitely no surprises if you do software development for a company that writes math libraries like NVIDIA, AMD, and so on. I am sure that nobody would dispute my reasoning here, but most software development doesn't actually deal with math like that. You maybe use basic arithmetic and that's it. However, that does not mean that all your math education is wasted. Quite the contrary, you still get to use your mathematical training just indirectly. Software developers do not just write code for the sake of writing code. They write code that solves some problems that a business needs solving. In other words, a software developer converts business logic into computer logic. Doing this conversion is actually a rather difficult task, hence the rather high pay of this career path. If you think back to what I said in the first part of this video, specifically about the mathematical approach to problem solving, you should realize quite quickly how your mathematical training is coming into play. Converting business requirements and logic into computer logic is basically the same thing as writing a mathematical proof. Just like in a proof, you cannot just hand-wave away parts of the code, the program just won't run otherwise. Similarly, you are rewarded by stating your assumptions and dealing with them ahead of time by having more resilient code that is easier to debug and maintain. Therefore, while you may not use your math courses explicitly when making yet another web page, you will benefit greatly from all the mathematical training you have completed throughout your degree. That's about everything that I wanted to say about how you are likely to use all your math knowledge after finishing your undergraduate degree. I believe that I explained quite adequately how while this comic is absolutely true, it does not mean that all the math skill that you built up throughout your CS degree is wasted after you finish your education. If you have any further thoughts on this topic or want to share how you use math in your career, then please do so by leaving a comment below. Oh, and while you're there, feel free to like this video, assuming that you liked it, and maybe even subscribe to my channel if you're interested in seeing more content from me. Thank you for your time. Bye.